Pluto is a far-off and bewildering planet, which was once an individual member of our nearby planetary family. However, continuous unsettling declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. With stunning openness, they proposed that this cold world is on a potential collision course with Neptune. But how could this happen, and what might be the outcomes of such a tremendous event? Are we seeing an interesting, boundless natural phenomenon? Or is there something else to this impending cosmic disaster? Join us as we explore the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet largely because of its erratic orbit, remains a subject of interest and study in the astronomical community. As shown by recent figures from leading experts, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potentially hazardous crash between these two planets, which could represent a significant risk to Earth. But how is such an event even conceivable? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It requires a stunning 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even finished one full revolution yet. The intrigue doesn't stop there. Pluto's orbit is marked by its particularly elongated shape, deviating greatly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination, which is set at 17 degrees to the ecliptic plane. The path Pluto follows is considerably steeper compared to the other planets. This inclination and erratic nature add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For nearly 20 years during each orbit, Pluto actually comes closer to the Sun than Neptune, contradicting what we might expect from their positions in the solar system. This prompts the usual question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to figure out its irregular orbit. Like other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out due to its steep inclination and elongated shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amid these complexities is a testament to the intricacies of celestial mechanics. The three-body problem in space deals with predicting how three objects, such as Pluto, Neptune, and the Sun, move and interact with each other through gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. For Pluto's case, this problem illustrates how its orbit, Neptune's path, and the Sun's gravity all work together in a complex way. The terms axial libration and nodal libration, along with zonal oscillation, are key components of this puzzle, as shown by astrophysicists. What keeps all planets in their orbits is axial libration. For Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is aligned at least 90 degrees away from Neptune. This spatial separation is crucial in keeping their orbits from crossing. Nodal libration, on the other hand, refers to the upward movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is situated well above their orbital plane, providing an additional layer of protection from potential collisions. Another key piece of this puzzle is zonal oscillation. This term, named after researchers Von Zippel and F., refers to how celestial objects like Pluto, Neptune, and the Sun interact through their gravitational forces. This gravitational pull affects their movement. For Pluto, zonal oscillation helps us understand why its orbit around the Sun is so unique. Despite the seemingly chaotic nature of Pluto's path, this oscillation helps it remain on a smooth trajectory over long periods of time. These factors assist in keeping Pluto's orbit stable, ensuring that it doesn't collide with Neptune or veer off course. Of course, this three-body problem helps us understand how these components shift based on the gravitational interactions of celestial objects. Studying this allows us to learn more about Pluto, our solar system, distant worlds, and their stars. Mathematical simulations in the late 1980s revealed that despite these stabilizing factors, Pluto's orbit is indeed turbulent, with slight deviations in initial conditions leading to massive changes over centuries. However, these peculiarities of Pluto's orbit have been shown to maintain stability over incredibly long timescales, effectively checking the chaos. Further computational models have helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto in which, for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This resonance helps stabilize Pluto's orbit. However, Neptune isn't alone in this. Jupiter's gravity also plays a significant role in safeguarding Pluto's orbit. In fact, Jupiter's gravity alone is sufficient to ensure that Pluto remains on a steady path for many years, even billions of years. So, it seems that Neptune, Jupiter, and Saturn are all working together to ensure Pluto continues its safe journey through space without running into trouble. These properties are significant in the broader context of the universe, keeping the order and consistency of celestial bodies' movements. Without these mechanisms, our solar system would be a much more chaotic and unpredictable place. Bodies like Pluto could potentially collide with others or be ejected from their stable orbits, leading to impacts on other celestial bodies. For Pluto, especially with discussions of it potentially colliding with Neptune in the future, understanding its orbit is crucial. It gives us a clearer picture of the dynamic nature of our local planetary system. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of balance through the complex negotiation of gravitational forces and orbital mechanics. It also highlights the importance of continued observation and study of these phenomena to better understand our place in the universe. Investigating the depths of space often leads us to confront the unpredictable nature of celestial bodies. Pluto's orbit is an ideal representation of this instability, demonstrating how orbital chaos, referring to the delicate dependence of a celestial body's path on its initial conditions, is particularly evident in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can drastically alter its long-term orbit. Using virtual simulations has been extremely helpful for researchers in determining how Pluto moves in space. These simulations use advanced mathematics to show how Pluto and other celestial objects like Neptune influence each other. By tweaking small details in the simulations, astronomers can see how even tiny changes can have a huge effect on where Pluto ends up. In the late 1980s, these simulations uncovered something truly interesting about Pluto's orbit. Despite having factors like axial and nodal libration to stabilize it, its path can still be wild and erratic. If you start with just a small difference in Pluto's position or the speed at which it's moving, over many years its orbit can end up looking vastly different. Still, even with this chaos, Pluto's orbit remains stable for extended periods, like billions of years. This means that Pluto's journey around the Sun has some sort of order to it, even if it might appear chaotic at first. Predicting cosmic events, especially when they involve irregular orbits like Pluto's, presents huge challenges. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainties. While mathematical simulations provide a powerful tool to understand and predict the future behavior of celestial bodies, they also highlight the limits of our predictive abilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or distortion can lead to vastly different outcomes, making precise predictions an overwhelming task. Furthermore, the chaotic nature of celestial orbits, like Pluto's, serves as a reminder of the ever-evolving and dynamic nature of the universe. While we've made great strides in understanding space, Pluto's case serves as a reminder that our knowledge of the universe is still limited. Understanding the gravitational impacts of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can significantly affect the stability and direction of other bodies within the system. So why are prominent astrophysicists just now raising concerns about a potential collision between Pluto and Neptune, despite all these intricate forces working to prevent such an event? Neil deGrasse Tyson, a renowned astrophysicist and a key figure in promoting cosmology, offers a unique perspective on the mysteries of our nearby planetary system, especially the captivating case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of celestial mechanics and the public's fascination with the dark spaces of space. His stance on Pluto's renaming is grounded in the continuously developing understanding of our solar system. He sees the renaming not as a downgrade, but as a significant shift in our evolving appreciation of the various bodies orbiting our sun. His approach to celestial mechanics is one of ongoing learning and adaptation. He sees the complexities of orbits like Pluto's as a sign of how much more there is to discover in space. The interest in these questions, particularly the potential interactions between Pluto and Neptune, highlights the dynamic and often unpredictable nature of our solar system. His work emphasizes that the more we uncover about space, the more questions arise, urging us to investigate further and refine our understanding of the universe. Michio Kaku, another famous physicist and futurist, offers an alternative yet complementary viewpoint on the mysteries of space, focusing on the often unpredictable forces that shape our universe. Kaku is known for his ability to connect complex scientific concepts with cutting-edge ideas, making him an influential voice in discussions about celestial mechanics and the broader implications for humanity. Kaku's perspectives on Pluto and its orbit highlight the need for constant observation and advanced models to predict and understand potential cosmic events. He views the interactions between celestial bodies as a critical area of study, not just for academic interest but also for practical implications. The potential collision between Pluto and Neptune, for instance, is not just a theoretical scenario but a reminder of the dynamic and often violent nature of space. Kaku's futurist viewpoint encourages us to think about the broader consequences of such events, from their impact on our understanding of the solar system to the potential need for future space interventions. Both Tyson and Kaku's views converge on the idea that space is a realm of endless discovery and that our current understanding, while vast, is still limited. Their emphasis on the need for continual investigation and advanced modeling reflects the evolving nature of space science. They highlight the importance of not just understanding celestial mechanics as they are today, but also predicting how they may change in the future. The potential impact between Pluto and Neptune serves as a case study for the larger challenges and opportunities in space exploration. It underscores the need for thorough scientific inquiry, advanced technology, and a willingness to adapt our understanding as new information emerges. For Tyson and Kaku, the mysteries of space, as embodied by Pluto's orbit, serve as a rallying cry for the scientific community and for humanity at large to continue pushing the boundaries of our knowledge. There is a general scientific consensus that in the distant future, the orbits of Pluto and Neptune will remain stable due to their mean motion resonance and the various gravitational forces acting on them. As a result, an actual crash between Pluto and Neptune is incredibly unlikely. However, the complexities and potential disturbances in their orbital dynamics mean that astronomers should continue to monitor and study these celestial bodies to better understand their long-term behavior and any potential risks they might pose. While the possibility of a Pluto-Neptune collision remains largely speculative and considered improbable with our current understanding, it highlights the importance of ongoing research and observation in space science. Advances in technology, including more sophisticated telescopes and automated insights, will help astronomers refine their models and predictions, ensuring we stay ahead of the dynamic and ever-changing nature of our planetary system. Tyson's perspective on Pluto's renaming, along with the emphasis on the unpredictable nature of celestial mechanics, underscores the need for continual assessment and a flexible understanding of our universe. The potential impact scenario, while addressing the dynamic and complex relationships within our solar system, ultimately serves as a reminder of the vast yet still unclear areas in our understanding of space. Through ongoing exploration and observation, we strive to unravel these mysteries, ensuring that our knowledge keeps pace with the ever-advancing universe. As we continue to delve deeper into the study of Pluto's orbit, it's important to consider the broader implications of celestial mechanics. The discovery of Pluto's unique orbital behavior has led to advancements in our understanding of the complex forces at play in the solar system. One aspect that has garnered significant interest is the influence of smaller celestial bodies, like comets and asteroids, on the larger planets. These objects, although seemingly insignificant, can subtly affect the orbits of planets like Pluto, adding yet another layer of complexity to the already intricate gravitational interactions. Another fascinating aspect of space exploration is the potential role of dark matter and dark energy in shaping the paths of distant objects. While we have yet to fully understand these mysterious forces, their potential impact on the stability of Pluto's orbit cannot be ruled out. The vast stretches of empty space between the planets are not truly empty. Dark matter and dark energy permeate the universe, exerting their influence in ways that may only be detectable with future technologies. Moreover, as our observational tools continue to evolve, the possibility of discovering more objects beyond Pluto, perhaps in the scattered disk or the Oort cloud, could provide further insight into the stability of our solar system. These distant bodies, many of which have orbits that may be influenced by the gravitational pull of larger planets, could offer clues about how Pluto's orbit has evolved and may continue to evolve over time. The ultimate goal of these studies is not only to understand Pluto's place in the solar system, but also to comprehend the dynamics of our entire cosmic neighborhood. The careful monitoring of Pluto, along with other distant objects, will help us refine our models and make more accurate predictions about the future movements of the planets. Through continued observation and technological advancements, we are unlocking more secrets of the universe, pushing the boundaries of our knowledge, and refining our understanding of the forces that govern the cosmos.